the hypothesis of ancient astronomical explosion is comprehensively recognized by most analysts as the fundamental explanation for the beginning stages of the universe, encompassing the creation of stars, planets, and all life, including us. No matter what its reasonably unconventional name, the term Big Bang appropriately captures the enormity of the event. At first, the universe was a thick variety of particles stuffed into a space more unobtrusive than a pinhead. From this minuscule point, a huge impact of matter happened, known as the Big Bang. This minimally summarizes the cycle that spread out over billions of years. However, despite the enduring predominance of the hypothesis of how things began, forms of progress in scientific data have logically tried its assumptions. When NASA shipped off the James Webb Space Telescope, the greatest and most advanced space observatory to date, specialists speculated that its insights would support the theory of the universe's origin. Unfortunately, later, after just 1 year in space, the telescope has confused analysts with its brilliant limits, providing momentous insights into the universe's past. The James Webb Telescope's discoveries have unveiled galaxies so advanced that they could reshape how we may interpret the universe's origins. This startling revelation has ignited serious interest among specialists and fans alike. One such vital discovery came when Space Master Rohan Natu, researching early images from the James Webb Telescope, unintentionally tracked down an incredible galaxy that blew many minds. This galaxy, named Glass C13, appeared to be bafflingly colossal and traced all the way back to just 300 million years after the Big Bang, making it older than any previously observed galaxy. Natu's enthusiasm was substantial as he shared the revelation with colleagues, describing it as surpassing cosmologists' wildest dreams. The James Webb Telescope, situated far from regular obstacles, was designed to delve into the universe's earliest age, known as the cosmic dawn. This time frame marks the formation of the universe's first stars and galaxies. By examining galaxies from this period, analysts hope to refine how they may interpret fundamental cosmic cycles, model the effects of dark matter and dark energy, and address early assumptions. Initial expectations for the James Webb Telescope's revelations were modest, anticipating several faint, distant astronomical systems. However, the truth outperformed all projections. The telescope's images revealed galaxies of astonishing advancement, challenging existing models and inciting a whirlwind of investigative development. As analysts continue to analyze the James Webb Telescope's data, the repercussions of these discoveries could be critical, ushering in a new era of cosmological observation. The unexpected findings from this outstanding observatory offer an enticing look into the universe's past, driving humanity's journey to unravel the secrets of existence. As early galaxies emerge, researchers and observers find themselves in a scramble to understand them. Could this gathering of oddly enormous and brilliant early galaxies be illusory, perhaps due to flaws in the assessment of the telescope's initial insights? Or, if they are genuine, could they somehow be reconciled with standard cosmological models? Alternatively, were they the first signs that the universe is stranger and more complex than our boldest theories had expected? In question is nothing less than our comprehension of how the universe we know ascended from primordial chaos. The early revelations from the James Webb Space Telescope might potentially enhance our understanding of the universe's history. These insights not only concern distant epochs and galaxies but also our own existence here in the cosmos. As Engraving McKieran, a senior member of the Science and Exploration Board at the European Space Agency involved with JWST, remarked, "You build these machines not to confirm the view but to break it, you just have no idea how it will break." One might say that JWST's observations of early galaxies have been billions of years in the making. However, more subtly, they trace back to the Space Telescope Science Institute in 1985. At that time, the Hubble Space Telescope was already 5 years from launch, yet the Foundation's then director, Riccardo Jamie, mentioned that his team began contemplating what could come after Hubble. Despite initial history debates focused on Hubble, Jamie was adamant about expecting the long-term development process. Then, Deputy Director of SD Sky, along with a small group, began drafting ideas for what eventually transformed into the Future Space Telescope, later renamed JWST. They recognized that while Hubble would be historic, its capabilities would be limited by its observations in visible light. The JWST, on the other hand, would observe in the infrared range, allowing it to penetrate further into the universe. The necessity for JWST became much clearer in December 1995 when cosmologists conducted the Hubble Deep Field observation. Not enduring assumptions of spotting just a few faint galaxies, the resulting image revealed countless galaxies stretching back over 12 billion years into the universe's history. After over 20 years of development and at a cost of around $10 billion, JWST was finally launched on Christmas Day 2021. The telescope underwent comprehensive testing before reaching its significant space destination a month later. By July 2022, it was ready to begin its long-anticipated first year of scientific observations, known as Cycle 1. A piece of JWST's early mission was focused on high-impact programs, including galactic evolution and early galaxy science, aiming to uncover insights into the secrets of the early universe. As astronomers devoted countless hours to examining small patches of the sky in search of primordial galaxies, they initially expected modest findings, similar to the puzzling interpretation of the Hubble Deep Field. However, they were in for a shock. Stephen Finkelstein from the University of Texas at Austin, leading the SE project, noted that incredibly distant galaxies were expected to emerge in various projects. Yet to the astonishment of space specialists, these galaxies appeared rapidly. At this point, the record for the most distant known galaxy belonged to GNZ11, observed in 2015 with a redshift of 11. Redshift measures the stretching of light due to the universe's expansion, with a higher value indicating greater distance. However, from the onset of JWST's observations, separate teams, including one led by Rohan Natu, quickly identified Glass C13, with a redshift of 13, pushing the cosmic timeline back significantly in their quest for rapid results. Experts relied upon modified strategies for crack evaluation, considering brightness assessments instead of additional time series direct assessments. Notwithstanding their ease, these assessments revealed universes startlingly mind-blowing and colossal, some previously boasting a great mass rising to 1 billion suns. Similarly, our own smooth way, which is billions of years more fostered, the energy didn't stop there. In the following days, different enormous frameworks, candidates from Burns and Glass, emerged, some with redshift checks as high as 20, exhibiting they existed a mere 180 million years after the colossal explosion. These universes showed circle-like plans not expected in such early cosmic ages. Moreover, another bunch tracked down confirmation of smooth-way oceans, universes at a redshift of 10, precisely 500 million years after the gigantic bang. Such a speedy ascent of sizable universes challenges the assumptions for the standard cosmological model, lambda cold dark matter. This irregularity ideas a brief return to early universe components in the fundamental moments after the gigantic explosion. The universe was a hot, thick soup of beginning-phase particles. Over the long haul, as the universe broadened and cooled, helium and other light parts formed, inciting the presence of the primary particles about 400,000 years later. Around 100 million years after the gigantic bang, conditions became accommodating for the game plan of the fundamental stars, made fundamentally of hydrogen and helium. These early stars were greater and more brilliant than current stars, amassed into protogalactic frameworks organized by the gravitational draw of dark matter. This discovery challenges the model, as it uncovers magnificent sizable universes far sooner than expected. Stacy Center from Case Western Reserve University noticed the surprising deficiency of different, more humble protogalactic segments, suggesting that a couple of seen universes may be closer than accepted, concealed by dust, appearing to be dimmer and more distant. The revelation of these early infinite frameworks raises critical issues about the universe's beginning phases, featuring the need for continued examination and revision of our cosmological models. Follow-up impressions of Glass C13, in exclusively later data cycles from August 2022 by the Atacama Large Millimeter Array, ALMA, in Chile, cast doubt on the hidden revelations, not enduring the usage of brightness-based assessments. ALMA didn't distinguish colossal amounts of buildup related to glass Z13. According to Tom B. from Goya College, who led the insights, this suggests that low redshift candidates can be dismissed. However, ALMA endeavored to perceive the enormous framework at this point, highlighting the trial of asserting perceptions made using JWST. High-level limits led Rohan Natu, one of the experts involved, to call attention to the incongruity of the situation. The potential gain news is there's nothing distinguished, he said. The horrendous news is there's nothing recognized with just JWST fit for circling back to its own insights. The most astounding explanation could be that the accepted LCDM cosmological model requires remedy. Michael Bone-Cullen, a cosmologist, expressed the degree of this potential change in perspective, communicating that these results are outstandingly astonishing and challenging to get in our standard model of cosmology. It would be a certifiable change to handle the dilemma. One sketchy recommendation is changed Newtonian dynamics, which challenges the presence of dark matter. JWST's discernments could lend support to these ideas, as proposed by various authors. However, not all stargazers are convinced of their validity. Another possible explanation is that early universe infinite frameworks may have had little to no buildup, making them appear more splendid and affecting mass calculations. This circumstance could also explain ALMA's difficulty in perceiving glass Z13. Charlotte Kraft and her partners suggested that JWST could be seeing the most splendid energetic universes in the early universe, which could indicate the most clear star formation conditions during that age. David Spergel maintains this thought, suggesting that high-mass star formation could have been even more efficient due to higher gas strains and temperatures, possibly impacted by early alluring fields. The rapid dissemination of new papers from JWST's initial discoveries mirrors a shift towards continuous peer review through platforms like AR14 and social media. While this speeds up the dissemination of revelations, there are concerns about rushing conclusions before thorough peer review, despite calibration issues and potential recalibrations impacting a few outcomes. The fact that all high redshift candidates made by JWST will be scrutinized rather than discredited suggests that the sheer number of these universes indicates the early universe may be different from what was previously expected. Finkelstein expressed hope in the authenticity of the revelations, communicating that the chances of astronomers being generally off base are small. Currently, space scientists are hustling to lead follow-up insights with JWST. Nancy Levinson is now reviewing around 12 proposals from various teams, searching for additional JWST observing time to explore high redshift framework contenders, given the enthusiasm and significance of these early discoveries. Space scientists are eager to confirm these crucial findings. Triu, who submitted one of the proposals, highlighted the importance of affirming these discoveries. Unique projects, for instance, the universe web led through Cartel-TE, are intended to substantially increase the known population of early frameworks by observing a greater region of the sky for a long time. TE checks that they might recognize numerous other universes, while additional efforts will seek confirmation of the first proto-universes, possibly used in the delicate deaths of supersized first stars and shining cosmic blasts as markers for their presence. A couple of assessments suggest that JWST could notice universes to the degree of a redshift of 26, just a short time after the gigantic explosion. Confirming even a small number of these high redshift contenders would be an earth-shattering achievement, as demonstrated by NATO. It is not to imply that space scientists are being misled by their insights. JWST has ushered in a new era of science, and despite the weaknesses, the rapid communication of new discoveries has invigorated the intellectual community. The question arises, is this present time the best opportunity to re-examine our perception of the start of cosmic history? Block Layer studies the critical repercussions of investigating the dark that closes the knowledge for the present. Make sure to show your support by liking,